Hello, everyone, and welcome to the fourth installment of the Genomics in the Cloud Book Club. I'm your host, KT Picard. In this installment, we'll be covering Chapter 3, Computing Technology for Life Scientists. I'd like to ask if you could, again, hold your questions to the end, if that's okay, because we have time at the end for an open discussion to go over anything that's happened in the lecture or in the last week as well. So this follows the format that we've been going through with the book club. Again, Chapter 3, and there's our byline for our two authors, and we'll go from there. So today's talk really is about the fundamentals of computing, and more kind of from a conceptual perspective. If these are, if you're coming at this from a genomics slant, then these ideas may be somewhat new. If you're a computer scientist, then a lot of this will be a review. But I've tried to incorporate information from the book, and also from some information from my background, which is generally more computing oriented or leaning than genomics, and to try to keep it interesting. And by the end of this, you'll have a good understanding of concepts of modern computing, essentially, especially how they relate to cloud computing, and also an introduction to Docker, which is really forms kind of the underpinning of moving into next week, the cloud computing and reusable code and that. So just some preliminary, just in terms, most of these will be familiar to you, but I thought we'd walk through them and relate them specifically to how they work in the genomics world. Most basic, of course, is the CPU, or central processing unit. There are other related terms like RAM and ROM and gigabytes and things like that. We'll presume that the audience has the background for that, and it's certainly lots of information out there for finding it. But the reason that we bring it up is that it forms the basis for the rest of these processing units or variations. So we move on from the CPU, which would generally be the thing that's doing most of the work for any processing that you're doing, to the other, kind of the next advance in this, which was the graphical processing unit, or GPU. Every computer that's sold today has both a CPU and a GPU, whether that GPU is on board inside the motherboard or it's on a card for gaming purposes. The reason for moving some of the processing to the graphics card is for increased speed. The big win here on these GPUs is that they do multiplication and addition operations very, very quickly. And you can see on the right there, we'll get to this tensor cube in just a second. But the tuples that you see over here with the surface normals, this is very important when you're computing light models, for example, in the gaming world, and you have an object like a cube, and you want to figure out the surface shading. And to get this orthogonal vector off of this surface, you use a cross product to get that vector. And the cross product is really just a combination of multiplication and addition of these two vectors that form the plane. So it does those operations very, very quickly, and it's why you'll see some movement. NVIDIA is a good example of moving some of these operations onto GPUs. We see these also in machine learning. We'll talk about that in just a minute. Next, the field programmable gate array, or FPGA, not used as much as it used to be. Field programmable in the sense that you could write code to it. Generally speaking, it's a low-level form of coding, microcode, which is an underpinning of high-level languages like C or Python, and then under that are the machine instruction set, the assembly set. And then generally under that is a set of microcode. These were designed to provide really high performance applications. There have been some genomics pipelines that have been implemented in FPGAs. They're hard to maintain. They are expensive, and so unless you have a very specific purpose for it, it's not used as much anymore. And so where most of the effort is going these days is into these GPUs, or the Google variant of this is called the TPU, or Tensor Processing Unit. You may have heard of TensorFlow, This is an open source machine learning package, and Google has developed chips that are specific to tensor processing. The kind of chip you'll see there is called an application-specific integrated circuit, or ASIC, as it's often called. And in this case, it does the same kinds of operations that we just talked about, these these tuples or pairs of vectors. In this case, what you're looking at is a stress tensor. And in certain applications, it's important to understand where stress is coming from on all three, in this case, the three visible surfaces. And really what we're unpacking here in this idea of a tensor is that it's just a collection of vectors of these tuples, and you can keep adding and packing them together. Mathematically, it performs a nice compact representation that we use certainly in machine learning, but also can be used in genomics. I think that's enough said about that. Okay. So from there, let's build on those ideas and talk about how kind of modern computing has evolved. This is kind of moving up into cloud before we get there. Some concepts. So on the very far left, you'll see the concept of the core, and you'll see above the single core CPU, and at the bottom the quad core. So for the last, oh gosh, it's been a while now, 10, 15 years, we've been seeing CPUs with multiple cores in them, or essentially additional CPUs within CPUs. You can think of it that way. And whether they have 2 or 4 or greater numbers of cores, it's a way of improving processing capabilities. And we'll talk about this in the next couple of slides of how that's done. So cores then are paired together with storage and memory. This is kind of the basic architecture of computing that we've known and love for years and years. And we'll move on to the right. Then when you put machines together, you can build a cluster. If you're not in a cloud environment, this is probably the environment that you have today. And this represents a bunch of machines or nodes, and then they're hopefully pooled together with a shared file system so that you can have access to the same data. Depending on the software that you're using, sometimes the network nodes can share memory across them. There's ways of doing that. There's message passing that allows you to move information between the nodes. And as you can see at the top, sometimes there's a node that allows you to schedule processes and then share them again across the nodes. So this is, again, in a non-cloud environment, how our things are usually done today. And you take advantage of this concept of parallelism by running the same job on multiple nodes. That leads us to this concept, and you can see on the top, this running tasks in parallel is one of the modern ways that we get faster throughput. And this is one technique called scatter-gather, where your inputs may be, in this example, multiple genomes. The scatter may be sending out those genomes to multiple processors, whether those processors are in different nodes or in certain computing architectures, those processors indeed may be in the same machine. So for example, in the world of supercomputing, you may find that there are multiple processors that have a shared pool of memory, or again, in others, these may be disparate machines that are physically located in different places. We'll talk a little bit more about multi-threading here. Just to introduce the concept on the right. Again, another relatively modern concept is multi-threading, which is how do we take a process represented by the blue line and then spread it across the cores of a CPU. And then again, we gather those threads at the end. We'll talk a little bit more in the next slide, but it's a way of speeding up processing, and it's something that you code for to make those improvements. Generally, the operating system handles the assignment and sharing of processes in the CPU. At the end of the processing, then you gather those results and you write them out. Sometimes the gathering is done by another program. and other places you write out the files to storage and gather them later. So a little bit more about multi-threading. As you can see in the green box, when we program, we can actually explicitly write a process and call it a thread. When we do that, we're taking advantage of the multi-core processing in the CPU. The threads there, 1, 2, and 3, represent 3 different tasks. And the point of this slide is that the threads can talk to each other and they can share information. Really what's going on here is that the threads are sharing, kind of time sharing on the cores themselves. And those threads can either be across multiple cores or just on one core. The reason that it's important is oftentimes the example we most often give is when we're doing things like doing a lot of number crunching in the background for genomics. And we want also, though, to have a visible window that would accept input, so that if you wanted to stop it or query a process, that you, for example, could have the query thread running here, you could have the processing thread running here, and then an output thread running here. And these are again, if you had just a single CPU with multiple cores, you could do it that way, or there are some systems that spread these threads across multiple CPUs as well. So again, it's a way of taking advantage of parallelism within the architecture itself. Another concept, if you're not familiar with it, is synchronous versus asynchronous computing. So this ties back into the last slide. In the absence of threading, what we generally have is synchronous computing or blocking. And what that means is that when you send out a request, you have to wait for the response, and that's represented by these blocks on the top. And then you move on to the next task, which is request, and then that request comes back. This is an example on the left and right. These are both examples of what we call sequence diagrams. And if they're new to you, I'd refer you to this website down here on the bottom. I found it very useful to create these web sequence diagrams. And it's a way that software engineers communicate process flow. In this case, on the right, you're seeing asynchronous, and what it means is that these things are independent of each other, and that request 1 and request 2 can happen on one thread, for example, and the responses could happen on another thread. And so that's another example of how asynchronous computing allows you to do more at once. Again, these are just concepts that help us move through the world of computing. Another one I wanted to bring forward was pipelining, and we hear this a lot, the genomics pipeline. And the analogy that we like to use is the car wash. And what you're looking at are 3 cars that are in 3 different stages of being clean. And the more cars that you can put through, the more efficient your pipeline is. And so there's an idea that we use in genomics that we're trying to move things through the stages. So whether that's aligning reads and then calling reads and then analyzing those reads, those are things that we can put together. And we can move those genomes in different stages. And we can also share some memory for that and improve processing time, because you can, of course, move more people through the car wash if you have a steady stream of cars that are waiting to have instructions operated on them. So again, just another basic concept. You'll see this practically, you may have seen this in the Unix world with the vertical bar. Sometimes you can string programs together and put the vertical bar, or what we call the pipe, between them. And then what that means is that the output of the first program is piped or sent into the input of the second program, and so on. So again, just a concept for computing. So building on that, the book goes into virtualization now, and this is where we're starting to talk about Docker and the abstraction of these computing ideas as we move into cloud. So across the top is how we started, which were a combination of technologies that were on your laptop or on a physical machine, and you can see the stack, or the commonly referred to as the stack here, which is just a bunch of boxes that are on the left. And along the bottom is the physical machine, or later we'll call it the infrastructure. There's an operating system that's part of that. There are binaries, which are compiled programs, or libraries, which are collections of objects that are used to execute a program. And generally speaking, those are then called by an application. And the application then uses the libraries on that operating system to do what you want to do. So in this case, run the GATK. It may have underlying code underneath it. So GATK is written in Java. And so that would be a library that you use to execute. And then under that would be the operating system. Some examples there, you see Linux, the open source version of Unix, or Mac OS. This is OS 10, right now the current version for Mac. And here's the kind of monolithic processor that we talked about before. So moving on, the next big advance, and this has been happening for at least 10 years now, is this idea of the virtual machine. A company by the name of VMware is the leading commercial implementer, and there are freeware versions or open source versions of VM as well. But the basic idea behind it is it's very clever. It uses the resources that you have and partitions them so that instead of having, even if you do have one physical machine, you can partition it into multiple virtual machines. And you'll see here in the diagram, there's the green, yellow, and kind of mauve different applications. And they could all be running different operating systems. They could have different libraries. The nice thing about this is that these things are separated by memory, so that you, generally speaking, if this crashes, your other apps still stay up and running. And this is a huge advance, not only for making things efficient, but also for allowing things to run without bothering other programs. There is a host operating system that runs underneath all that. And there's this new layer that we introduced in the VM world. This is called the hypervisor. It goes by many different names, but it is the management software that runs the virtual machines and allows you to partition a virtual machine to, for example, migrate information from one to another. Hypervisors allow you to have, for example, a high availability, so that if one did crash, you could automatically move over to another. Lots of management there and flexibility. So finally, we virtualize this one more time, and we abstract out the applications into these things called Dockers or containers. Docker is this idea of containerization, or a collection of an application in a standards-based way that can be moved in and out easily into your computing environment. The concept behind it is, you may have heard the word microservices, and these services then allow you to use standardized bits of code that are reusable. And that's exactly where we're going with this class, is to talk about the GATK versions that are so-called Dockerized, that allow us to bring in that code from somewhere else rather than compiling it natively on our system and running it there. So we've changed the infrastructure a little bit. We've added this Docker daemon, or program that runs in the background, that allows us then to bring in these, this little blue represents the Docker container. But the rest is the same. We still have other underlying libraries like Python or R or Java running there in the background. Our applications are built on top of that. But there are things like GATK, for example, that are containerized and allow us to operate without having to, again, bring in the code ourselves, compile it for our specific operating system. The Docker doesn't assume that there is an underlying operating system. This is an important differentiation. In the VM world, usually the VM includes the operating system with it, so it tends to be really large. I mean, on the order of tens of gigabytes. The Dockers tend to be much smaller, and the reason is that you're leaving out most of the underlying operating systems and infrastructure and leaving that to the host of infrastructure to provide. So it provides, again, this microservice idea, or a lighter service or lighter weight service method. And you can use all these together. So here we've kind of put this whole concept together where we're using virtual machines along with Dockers. And again, let's just unpack this a little bit. We have now different applications running across from left to right. You'll see in the first virtual machine on the left, this is a Dockerized environment with two applications running in this virtual machine. The one in the middle is simply running one Docker application, and the one on the right isn't running Docker at all. So in this VM environment, you can mix and match Docker applications, Docker-based applications with non-Docker-based applications. And this all works nice and seamlessly together. A little bit more about Docker. This is the symbol, this is the icon for Docker. I mentioned earlier that the Docker images are generally speaking hosted in a registry, and we'll cover some of those in a later slide. But this is a place, for example, where you'd pull GITK from a registry, you'd pull that into your computing environment. This is called a Docker image. There's actually a command called Docker run that allows you to run this container in your compute environment. It does sit in storage, so once you pull it over, it sits there until you're ready to use it. And so again, it's reusable, so you don't have to keep pulling it over and over again. Creating a Docker image then is relatively simple. There's something called a Docker file, which is a manifest of things, or like a list of things that have to be put together into an image. It's then stored into a container. That container then is pushed out to the registry, which is how this code then is reused or reusable by others. And that's the general process for making this reusable code that now in the cloud environment, as we move to cloud, makes it so appealing and kind of the basis for a lot of what we'll be doing in the rest of the book. Some additional resources. I mentioned registries, so there are a few that are discussed in the book. I'll leave them there for you to explore. There is one more that was mentioned. If some computing environments would not allow, Docker. I know some of our members would have some challenges working with cloud computing environments. There was a mention of something called Singularity, which is an alternate to Docker, which I believe has additional security measures, so it would be worth looking at. I've included some basic information if you'd like to learn more about Docker. These are not endorsements by any means. Some of these have small costs associated with them, but I included them just for completeness. So there's some on Docker there, some on learning Linux from MIT, and Linux for beginners. If you'll see, Linux kind of is the underpinning for most of what we do. And so being able to maneuver through the operating system, you'll see in our next coming chapter on cloud, you'll need some kind of familiarity with the Linux operating system. And so I would recommend those resources to learn a little bit more if it's new to you. And that'll become really apparent in our next chapter, and chapter 4, where I'm very happy to say that we'll be having a guest speaker. One of the authors, Dr. Geraldine Vander Ora, got it right this time, will be presenting chapter 4 on the introduction to cloud computing, and very happy to have her join us for that. So I'll pause there. We've covered a fair amount of material in a short period of time, just like last time. So I'll pause and I'll stop my sharing, and we'll go for questions.
Hi, KT. Thanks for the great recap. I'm just wondering, in your experience, have you worked with TPUs or FPGAs?
So have I worked with FPGAs or no? So TPUs are going to be specific to Google Cloud. So we'll see those when we get to Google Cloud. FPGAs, I think I have probably in the course of my career. I think probably the most common, I think the Dragon genomics pipeline was initially implemented on FPGAs. And I think that's probably the most commonly thought of application in genomics that I'm aware of. You know, you'll find them even like in your automobile. They refer to the chips that are, you know, either FPGAs or ASICs, which are very, very specific. But sometimes, you know, those chips are reprogrammable. And so really the FPGA is this notion that you can change them. You know, again, it's a little tricky because physically you have to make the change to the code. But, and like I said, they're kind of falling out of fashion because software is becoming so much faster that it just doesn't matter as much anymore. The tensor processing unit is, or GPUs for that matter, are really kind of coming into their own, and that's why you see the meteoric rise of them, especially in machine learning. Because they are really good at special purpose processing for you know, particular types of operations. Does that get at your question?
Yeah, it does. Thanks. We were actually talking in discussion. I'm just looking on Slack here. I think one of the members, Amin, I might have got that wrong. We were talking about Dragon GATK, and they're actually releasing it here in the first quarter of 2021, open source as well. So you can run DragMap and their variant caller on FPGA architecture, or I believe just on your typical server. Same code, same results, but just different architecture underlying to kind of attract people, probably because it's difficult to have access to these.
Precisely, and I think there was a little chatter on Slack this week, and Geraldine was chiming in about the release of that software, and I think that's one of the areas that the book will probably expand, is to incorporate that pipeline in future versions. So I'm sure that'll be a big, you know, a point of discussion on Slack over the next few weeks, is because it is coming up soon, and people want to know how they can, you know, get faster throughput with that code. So yeah, thanks Ian for I'll post this in afterwards. I'll post those links into Slack so that if you're not joining us here on the Zoom call, that you'll be able to get access to the links. Other questions? Well, I'll throw one out there. You know, in looking at the Linux operating system, you'll see the version, it comes across in the book several times. You'll see Linux version 18 LTS, and the question is, what the heck is that? And it simply means it's the current version of Linux that's being offered by a cloud vendor like Google or Amazon or Microsoft. There's even a version 21 that's out there, but the LTS stands for long-term server. And what it means is that it's expected to be supported for, I think it's 5 years, I forget, but without having to make major changes, so that you don't have to go change the underlying operating system every few months. And so what it's saying is that the community, the open source community, is committed to supporting that particular version. And that allows us to, you know, rather than changing our operating system, we all know how long that takes. It allows us to make changes less often and to provide some continuity. And that allows us to take a look at some of these questions over here. Let's see, from Mikhail, if I understand correctly, the Google Pipelines API will automatically run additional VMs to match the required hardware for our jobs. Yes? Does that mean that we will not encounter memory allocation errors like if we're working in a shared cluster? Well, I'll take a stab at that, and then I'll let others chime in. The idea behind this, and we'll get into it in the book, you know, there's a programming language called Cromwell that I know nothing about other than it has a name, that indeed allows us to scale up the number of processors in the cloud. So if you have tens of thousands of genomes, the promise is that by using things like the pipeline API, that you can scale. And that's, again, one of the benefits of going to cloud, is that you can just add additional processors or memory as needed. And so to your point, yes, that's why you would not run out of memory, because in a cluster, you generally have a fixed amount of memory and those resources are not expandable past a certain point. whether your cluster is governed, as in you can use 4 nodes and that's all you get, or let's say you have a 16 or 32 node cluster and you just fill it up. That's again one of the huge advances in cloud computing is this idea of burstable, or elastic is another word that's used, of computing. I'd love to have others chime in on this. Thoughts about your experience with expandable cluster. Honestly, I'm gonna love doing this. I've done all my work a lot of work in the cloud, but not with pipelines that allow me to on demand burst to greater numbers of CPUs. Anybody else have experience with that?
I have a little bit of experience with AWS Batch and friends, and I think the principle is similar. There's one failure mode though that annoyingly often comes up, which is that you have something like a Docker container that takes more memory than what you've budgeted for, because your Docker container still has to run on a VM that is spun up. And maybe your job halfway will run out of memory given that VM, and you have to restart it on a larger VM. And that's sort of like, you still have a little bit of that trial and error, like, okay, I'm doing a genome assembly, so I probably need to budget for a VM that will have or a set of VMs that will have a large amount of RAM. But at least you're not constrained by the limitations of what you have in-house, and you can turn the dial if it turns out to be a problem.
Exactly. Well, you bring up a good point, Joris, which is it does cost money when you do add additional compute power to your problem. One of the things I came across this week was when you're setting up your Google Cloud environment to put an alert. As you noticed in the book, if you've gone ahead a little bit, you have a $300 credit, $300 credit for running your genomics applications. You have to take down that credit or use that credit within a 1-year period. And there was a suggestion to put an alert so that if you've used more than, let's say, $50 US dollars, that you know about it. And I thought that was a good suggestion. I think Geraldine will probably talk next week about turning off your processing environment when you're not using it, so that you're not charged for cycles that you're not you don't need to use. Again, we're probably all trying to be very budget conscious if we're doing this on our own. But yeah, again, keeping track of how the CPU usage is being handled. So a practical idea is set an alert. I'm sure Geraldine will share more of this next week. More in the chat window. I'm gonna have to ask what a Slurm scheduler is. I don't know what that is, but the question from Matthew was, does it mean that we would not have to specify wall time and memory like with a Slurm schedule? So yeah, so I'm gonna ask. I think probably we'll just talk about it a little bit. Please let me know what a Slurm scheduler is, and let's build on that.
Yeah, sorry there, KT. Slurm scheduler is probably like Cromwell. I think I was misinterpreting Michael's question there about bursting and specifying architecture. So nodes, cores, that sort of thing, where I was talking about specifying the wall time. So the requested length the job is going to run for, how much memory. So this is something we typically use in HPC environments. There's also LSF, which is an IBM tool, SGE for SunGrid Engine. There's a bunch of them out there.
Cool. HPC, high performance computing, if that's a new acronym to use. So in computing, the most of the secret to understanding genomics is decoding the acronyms, right? And so we spend a lot of our time, engineers love to take concepts and turn them into 3- and 4-letter acronyms. And so it's acronym rich. And so again, not to be intimidated by that. The nice thing is it's just easy to Google these things now and get it. I just want to echo Ian's comments. Thank you so much, Ian, for the additional information on By the way, do we pronounce this dragon or dragon? I've never been sure. Anybody? Preferences?
It's
I don't know.
dragon. It's
is
dragon.
it dragon?
And
Okay, all right.
I shared the name wrong. It was Amit Rupani. He's got some stuff in Slack. You can look. There's a webinar that they shared in November, I believe, for Dragon GATK. So you can tune into that if you're interested.
Cool. Hey, thanks for that pointer, Matthew. So yeah, Ian really characterizes it nicely. As I mentioned, Illumina uses the FPGA version. The version that's coming out through Broad is an open source version, and it runs on a CPU. And that kind of echoes my earlier comment, which is software, the processors, the CPUs are fast enough now that it's you can gain additional performance through FPGAs. Another company called Sention, also has provided GATK versions that are more performant. Again, not all these things use, sorry, a lot of these things just use now standard GPU processing. Or sorry, CPU combination CPU GPU. Okay, let's see. Results for this one. Great. Okay. Good. So good discussions. This is again, this is exactly what we're trying to get at is together learning the ins and outs of what's coming and how we'll be using these things in future. That's great. Other questions before we before any questions on computing before we move on? Okay. Great. Well, I want to spend some time, and we've got new members on the line with us today. We added, if you saw on Slack, we added 8 members in the last week, and so we're up to about 25. We're excited about the additional people who have joined us again from around the world. And one person that I can see that looks new to me is someone mentioned Stu, but I think he or she just dropped, but. Or maybe just got lost. Okay. Stu, are you there? Ian, is this someone that you know or someone that works with you?
No, I don't know him. I don't know the STU10. Yeah.
Okay. Okay. I think we lost him, but it's okay. Yeah. I'd like to give everybody a chance to say hello. Great. Great. Okay, so also just want to bring everyone's attention back to things over the last week. We've had really interesting conversations about base quality score recalibration. We've had discussions about what is a read group that came out of the meeting last week when we were talking about different kinds of genomics files. We had Amit put some information about the history of the Human Genome Project and some videos and book recommendations. We continue to, we've got new members that have joined as we speak here. And again, just really excited about all the excitement around people joining up with us and following us now, not only on Twitter, but also on YouTube, where we post these videos after the meeting. So I'll pause one final time. I think that's going to wrap it up for this week. This kind of concludes our intro series. We've spent the first few meetings getting a background in genomics, getting a background in computing. I hope these background concepts have been useful to you. Other thoughts from the group before we wrap up today's call? Questions or things that you saw in Slack that you'd like to explore further, or conversations or topics you'd like me to cover between now and next week when Geraldine takes over? I'll give you one. So,
sorry.
Please. Yeah, go ahead, please.
I thought it would be interesting just to get a feel for where everybody's at. There's a few technologies that have been mentioned in this chapter, and it'd be interesting to hear a little bit from everyone, like which technologies they've used before, like what are they kind of familiar with? Have they tried Docker, for example? Are there any DSLs that they've had experience with that. I think that could be interesting as a
Yeah,
closing.
Sure, let's take a few minutes. Experience with cloud computing in general, Docker more specifically, and then even finer than that, specific things that you used in Docker in genomics or other, let's say with something else. Matthew, I'm assuming that, well, I'll ask you to kick it off. What's your experience then?
Yeah, sure. I kind of, oh, wrong Matthew. Go ahead, Matthew.
Yeah, okay. Well, I've since I've used the Terra platform before, I've have some experience with Whittle, which I think probably other people have experience with other DSLs rather than Whittle. But I'd be interested to see if anybody has had a go at Whittle. And in terms of Docker containers, I've done some training, but I've used them, but I haven't made any or something. I suppose there's a difference between using them and making them. For Whittle, I've both used Whittles and also written some of them. Yeah, so I'd be interested to see if anybody else has what other people's experience with that is.
Great, Matthew, thank you. So Whittle, of course, is the workflow design language. It features heavily in the book. It's one of several, flow languages that allow you to sometimes pipeline, but also to set up a process of commands together. There was a discussion on Slack around different design language tools. So, for example, SnakeMake came up a lot, and there was a Twitter post. Matthew, I'll go over to you, and maybe you can talk about your experience with SnakeMake. And there was this question from Dr. Niels on Twitter about tasks and subtasks, and maybe you could talk a little bit about that and kind of elucidate that for us. Yes. Matthew, can you hear us? Did I lose you?
Yeah, sorry. Can you just repeat the question one more time?
Yeah, sure. So no problem. So I was asking about, so we were talking about different kinds of workflow languages, and I think SnakeMake is one that you'd used. There was a reference to a Twitter post on Slack in the last week. Dr. Niels had pointed out different workflow languages, and one of the comments was, do these languages have the ability to do subtasks? And the question was, he wasn't sure that SnakeMake allowed that. Wonder if you could talk to us about that. Also, I think there's some chatter about incorporating other workflow languages inside of Terra. So we can chat about that too.
Yeah, so I've had experience working with SnakeMake. It has its own, well, it uses a real programming language, Python. As far as I know, Whittle, which we're using in the book, kind of invented their own language. Whether that's good or bad, I'm not sure. I'll find out for myself and make my own opinions, I suppose. As far as that quote from Dr. Nils Homer, I think there was probably some terminology we should cover. Geraldine quoted in that the sub workflow is kind of misleading, possibly. Basically, he was just kind of highlighting the way these tasks are broken down, I guess. So in SnakeMake, for each rule, so you might have, let's say, the alignment be a rule, and then have mark duplicates be another rule. In Whittle, these would be called tasks, and it's just breaking it down into the steps in the pipeline, like in your analogy for the car wash, I believe. As far as what sub workflows are, as I understand it, is the ability to import other workflows that people have written already, so a pipeline, into your workflow. So instead of an individual rule, it would be running its own workflow. And this can be done in SnakeMake and Whittle. As far as I understand, the Whittle and CWL are a little bit more advanced. They can do a little bit more in terms of flexibility than SnakeMake, but where SnakeMake kind of shines is a lot of people are familiar with the Python language, so it's an easy entry point, I believe.
Exactly. Great. Thank you for that. And I see in the Slack channel that you've been working with Amazon EC2 or the Elastic Compute Cloud. The C2 is Compute Cloud. And you mentioned Make and SnakeMake. I'll just, in case those are new terms to you, so Make is a Unix program that allows you to string a bunch of commands together, typically to compile code. So if you're writing, say, for example, C or doesn't matter, Python, you put a chain of commands together that allows you to execute a script or set of commands together. So you'd say make and then follow it with the name of your script file, and then executes those in turn and goes through and until you get to the desired state. I'm assuming that SnakeMake is just a more sophisticated version of Make. Is that am I overgeneralizing here, Matthew? Yeah, okay, great. So there we go. So Matthew just said yes. Thanks for the suggestion, Matthew, to ask. Let me pose one more question before we do wrap up. I have experience with Amazon. Looks like Matthew does as well. Does anyone have experience with Google Cloud Platform before this book? Has anyone used it before? Yeah, or Azure is another question. Either of those. So it looks like Matthew's used Google before.
Yes, although I would say 95% of the time in the context of using the Terra platform. But I have then gone on afterwards to kind of like test it out and see, get a feel for it without using Terra. Because obviously it's a very different experience if you're kind of using Terra on top of the Google Cloud and using the Google Cloud directly.
Sure. Understood. Anyone else like to share cloud experiences? So Ian's sharing information about workflow processing developed by a colleague that does tasks like Terra, and he's posted the GitHub link to that. So I'll, if you don't mind, Ian, I'll share that with the group as well on Slack. So thank you for that. Well, good. So again, we're kind of all ready to go. We're teed up for Geraldine to join us. I'm again thrilled that she's been chiming in a lot on Slack to keep us on track. I would encourage everyone between now and next week. This is one of those times you'll want to read ahead in Chapter 4. If you haven't yet, it's a good time to get your GCP account set up. It's relatively easy to do if you have an account on Google or if you're using Gmail. It's very easy to turn on. As I recommend putting a, make sure that you're not spending any more than you think you are, even though the dollars are free for the first $300. So that would be good for us to get, in preparation for next week. All right, any last thoughts from the group before we wrap up today's call? Good. Thank you. I appreciate the discussion. Okay. Well, at this time of year, I just want to thank everyone for joining. It's a very busy time of the year, but we're going to keep going at a chapter per week. And in whatever way that you keep the holidays, I wish the best to all of you, and appreciate so much your time today as we went over the concepts of computing for life scientists. Thanks for joining.
Happy holidays, everybody.
Thank you, and Merry Christmas.
Happy holidays and Merry Christmas to you all. Thanks.
Happy holidays. Bye, guys.
Bye-bye.